If we look at our setup where we're firing charged particles into a region where a magnetic field starts, we notice something interesting. We know there's going to be a force, in this case, to the right on this particle the whole way, and it will eventually come out the same way it went in. It'll come out going the opposite direction. It'll just do a 180 and come out. The distance between the point it enters and the point it leaves would be 2r, and we've already found r is mv over qb, just from our Lorentz force equals centripetal force. So what could we do with that? Well, the size of the radius here, the size of the separation between these 2 points, depends on the particle's charge, velocity, and mass. So Q, V, and B. During World War II, one of the big projects, obviously the biggest one, was making atomic bombs. And one of those bombs required uranium-235, and that's only about 7 parts in 1,000 of natural uranium, and it's all mixed in with uranium-238. From chemistry class, these are two different isotopes of uranium. The fact that they both have 92 protons means they're both uranium, but one has 143 neutrons and one has 146. They need to separate these two kinds of uranium because U-235 will make a bomb and U-238 won't. Unfortunately, since they both have the same number of protons, they have the same number of electrons, and they're in the same places, chemistry is mainly just moving electrons around, and that means we can't really separate isotopes using chemistry. There would be all sorts of ways to separate gold from iron using chemistry, but we can't separate one isotope of uranium from another. To make the bomb, we have to separate them physically. So the Manhattan Project used these devices. What we would call them now are mass spectrometers, although the ones now are much more elegant. But the difference in behavior of the two isotopes going through them allows you to separate the two isotopes. The heavier isotope will have a larger value of R, and it'll make a larger semicircle. So if we exaggerate this a lot, we have the same value of Q, same value of charge, same value of V, but slightly different values of mass. So we notice the lighter isotope, the U-235, goes here, and the heavier one, U-238, goes here. So we can imagine the simplest way to think about this: put a bucket right here, and you'll catch the atoms you want, have a different, basically a garbage can here to catch the other ones. The reason this job is so hard is they're separating uranium on the atomic level. They're firing these things in, and they're basically being separated one atom at a time. Many of them per second are going through here, obviously, or they never would have gotten it done. But still, it's a very time-consuming, energy-intensive process. The way to make an atomic bomb using U-235 is not difficult at all. It's a very simple engineering problem. So the difficulty in making a bomb with this stuff is enriching the uranium, not building the bomb. And whenever any other nuclear powers in the world, or perhaps your neighbors, find out about you separating uranium, that's when there are usually airstrikes. Now, instead of single moving charges, it's a lot more common to deal with currents, which are many, many charges. How would we find the force on a current carrying wire that's in a magnetic field? Well, we use the fact that the current I times the length of wire L is going to look a lot like a charge Q multiplied by velocity V. So we can write the force on the wire is I L cross B, where L is the length of wire. We could then write that as ILB sine theta, where theta is the angle between the wire and the magnetic field. The direction we find using the right-hand rule, same way as before. So if we point our fingers of your right hand in the direction of the conventional current, remember this is pretending it's made of positive charges, we curl them in the direction of B, the thumb points in the direction of F. So if we look at a current loop in a magnetic field, we'll see something interesting. We look at this figure, we imagine we've got a battery here, current going this way, then up, then back that way, then down, back to the other side of the battery. And we could say we want to know the force on all sides of this rectangle. On the bottom side and the top side, the current is going anti-parallel and parallel to the field. So theta would be either 0 or 180. Sine theta would be 0. We wouldn't get a force on the top and bottom. On the sides, though, there our angle is 90 degrees, so our force will be I times L times B. It won't be 0. What will the direction be? Take your right hand, point your fingers up, and then curl them this way to the right, and you'll see your thumb points into the screen. On the other hand, if you take your right hand and point it down and curl your fingers to the right, you'll see your thumb points out of the screen. So there's no net force here, but there's a net torque. The right side of this loop is being pulled out of the page and the left side is being pushed into it. So if we measured from the center of the loop, we could say W is the width of the loop and L is the height of the loop. Our torque is going to be force times lever arm, which remember is from the center, the axis of rotation, out to here. So this will be W over 2. This will be L. We'll have W over 2, ILB, and we've got two signs. We've got one sign that is the angle between the magnetic field and the current, and then we've got one sign that's the angle between this R and our force. Now, currents I2 and I4 are vertical, the magnetic field is horizontal, so no matter how much the loop spins around this vertical axis, this theta will be 90. So this goes away. Also, both of these torques are trying to rotate the loop the same way. So they add, and we could say the total torque is then 2 times this. So we've got 2 W over 2 ILB sine phi. Phi is the angle between the lever arm and the force. This is 90 degrees here, but it will change as the loop rotates out of the screen. It will eventually go to 0 when the loop has rotated so that we're looking at this edge on. I4 is as close to you as possible and I2 is as far away from you as possible. So the torque will be IWLB sine phi. WL is just the area of the loop, so I could say it's IAB sine phi. What if instead of one loop we have many loops of wire around here before we reconnect to the battery? Then we get a much larger torque. For n loops, the torque is going to be larger by n. So we can say the torque is NIAB sine theta. There are actually very clear similarities between this and the torque on an electric dipole. We can say the magnetic dipole moment looks like this, NIA, and the torque is mu cross B. Then we get exactly this for the torque. Once we rotate the loop 90 degrees, the picture looks like this. So if we're looking to the left from the right side of the page, what do we see? Now our currents are moving like this. Where are our forces? Here on the I1, for example, our current's moving down, so point your fingers down, then curl them out to you, you get a force to the left. Here on the bottom side, current's moving to the right, so point your fingers to the right, but curl them out of the page, you get a force down the page. Over here, current's moving up the page, point your fingers that way, curl them so they point to you, you get a force to the right. And finally, current moving to the left, point your fingers that way and curl them out of the page towards you, and you get a force up. So here, all those forces are just trying to stretch the loop. There won't be a torque anymore. Now all the forces are in line with the center of mass of the loop, and all it's trying to do is stretch it. So the current carrying loop acts like a bar magnet, and here the field of this bar magnet would point into the page. There's going to be a new right-hand rule associated with that. What if we replace our loop with a bar magnet and see that the magnet would give us the same magnetic field we had before? So here is our first picture. Now if we do this with bar magnets, let's imagine we hold this magnet here and let this magnet on the right spin. This is what we start with. And then this magnet will spin around this gray one so that the south end is as close as possible to the North Pole. Now, why is this useful? Well, what if we look at a little bit different way to wire this up? Instead of just directly connecting wires to the battery, what if we have these loops and brushes? These C-shaped pieces are called commutators, and these blocks here are called brushes. Notice as this hoop turns in the magnetic field, when it turns around 90 degrees so that it can line up with the field, then the current will be broken, the circuit will be broken, and there won't be any current through here anymore, and the field will stop. But because of rotational inertia, the loop will keep going. When the contacts jump from one side to the other side, now the loop gets a different push. It's going to continue to be pushed around and around and around. Every time the wire leads here go over the break in the commutators, the current changes direction, but since the loop has changed orientation, it's still getting pushed the same way over and over again. This is a motor. This is going to turn electric energy into mechanical energy, and it's obviously incredibly important for our lives today.